So our next talk is JV, who was at the University of Newcastle, but is currently in Brazil. So take it away.
Okay, thank you. Thank you for allowing me to give a talk, Kane. And today this topic is something that I started working when I was in Newcastle before coming back, but I didn't touch it that much. I still have the definitions, and I think it will probably work out well because it's related to what I did on my thesis, but I'm just trying to generalize the construction and changing a bunch of the things. But the main objective is, describing some big iterated wreath products. And even though the focus is t.d.l.c groups, I think just to make it easier, you can also think about them as, if you are not familiar with topological groups, as wreath products on discrete groups. I won't go too much into I will have the definitions for t.d.l.c groups, but it's not necessary to apply this just for, even the discrete groups are t.d.l.c, but you can think just about a group without a topology. So just to give an outline of the talk, first I will just give the definition of wreath products for the ones who don't know, and also describe what is the main goal that I will have, because I will have some ordered forests, so a bunch of graphs and arrows between vertices, and I want to use actions on these graphs to build groups that will have the nice properties that I want. I want them to be groups that are just iterated with products and that I can work with in the end. Then I will define the main definition that I'm working with at the moment, which is pre-wreath. And if anyone has any suggestions on changes of names, I'm okay with it, because at the moment I don't think all the names are as good as they can be. And then I will finally define what the groups are. But I want to talk about the topology on them. I already know that they can have a nice topological structure, but I won't talk about this at this talk. So first of all, let's, like I said, I'm defining the wreath product for t.d.l.c groups, but for discrete groups, you don't change that much. So the idea, the restrict wreath products of t.d.l.c ISC groups, so totally disconnected, locally compact, and second countable, TD for totally disconnected, LC for locally compact, and SC for second countable, which is just, it has the cardinality of the real numbers, or less than it. So you have a t.d.l.c group L, you have KX t.d.l.c SC permutation group, so it's a t.d.l.c group acting on a X is a countable set. And you usually act with compact open point stabilizers, which is a kind of nice-ish property. And then you have a compact open subgroup of L. So for the ones who are familiar with t.d.l.c groups, we always have compact open subgroups by the Van Dansk theorem. And you can define the pre-wreath products as just, you have a product of copies of L indexed by a set X, and you have K, your permutation group, acting on it by just shifting around. So just to give a simple idea, like in this case, like I said, just talking about, discrete groups, let K be just the group with the cyclic group of order 4. Let L just be the symmetric group with 3 elements. And our X will be just it will be just K. You are just acting, K is just acting on itself. So the wreath product, you will just have 4 copies of L, 1 for each element of your set X. And your K will just be acting by shifting the things as the group would shift the set X. When we have t.d.l.c groups, we also want these compact open subgroups, because we want to preserve our t.d.l.c topology. Like if we don't define them in a nice way with these U's, we easily lose our locally compactness. And in this case, yeah, you might lose second countable as well. Yeah. I'm not sure. And now just to give an example of how I want to work with things now. So now K and L are the same group. I just have the cyclic group of order 2 acting on itself as well, right? So what I want to visualize, the tree that I want to visualize, on each level, I will have, so here I just have 3 groups. One, it's an iterated wreath product with 3 groups, right? So I have the outer one, which just acts on 2 elements. The middle one, which you have 2 of them. So one is acting on this part above, one is acting on this part below. But this one can also move both of them, right? So I can, if I make an action of this, I can move this to here and the other one back. And here it's the same, like I have that these 2 are acting on this because I can move this up or down. Or this one can also make this go to this side here as well. So you, how do you say? I'm trying to see, I'm trying to describe the actions that each of these groups have by looking how they will move these vertices on the tree. Like I have what I will call my horribles, which are, which each of my levels will act on one of these horribles. So here I have that the black one is just acting on the black one, the blue one is just acting on the blue one, and the pink one is acting on the pink one. And I want to be able to define what the movements on these groups are in such a way that I can just restrict to the ones that are nice enough for me. They are the ones that are like these groups. They here there is it's not possible to do another morphism, but if I had 0, 1, 2, and 2, right? And I have just the cyclic group of order 3 acting on it. Here I wouldn't be able to just swap these 2 around because I just want an action of the cyclic group and leave the 2 still. So I also want to describe my action in such a way that, you know, my group can only act on these levels as these groups that I have here. Now that I have a brief description of the idea, I will talk about one of the concepts that I want. So now already talking about the pre-wreath forests. The idea is that here I had just 1 tree, right? 2 trees actually. But now I want to make, to describe a wreath product of 3 groups. Now I want to describe countably many of these wreath products. So I want to be able to have, you know, like for example, a line of the integers and just do an infinite wreath product that I go with all numbers indexed by the integers. So it's infinite on both sides. And to go on the more general case, what I want is what we call a discrete totally ordered set without endpoints, which is you have a partially ordered set with some order, a successor function. So you can go forward 1 step, a predecessor function, you can go back 1 step, and your order is also a total order. So everything is comparable as well. And here are just the properties that you expect from predecessor and successor. So there is no end. So you can always go forward, like there is no end forward, there is no end back. And you don't have maximums or minimum elements. So you don't have endpoints in this case. And in general, these ordered sets, they can always be seen as, you know, ordered set, let's call it O times Z, but with the lexicographic order. So any totally ordered set times Z with the lexicographic order will be set of this way. And all sets described on this way are also a set of the form O times Z, where O is a totally ordered set. And now for the definition of the trees that I want to, the forests that I want to build. For the ones who already saw the construction of the groups EXGU or PXGU that I had on some previous talks, the idea is that I want to, when I have L equals to Z, I want to build a, let me show that a drawing. I want to build an infinite tree that goes each vertex has countably many leaves coming to it, and it's an infinite tree. So here I have this middle line would be like a copy of the integers. Like here I have countably many ordered things like the integers in it. And for each vertex, I have countably many things pointing to it. Here I have just 3 pointing to each vertex, but I want to have as many as the natural numbers pointing to each vertex on your tree. And instead of just describing this tree, what I want to describe is as functions from my totally ordered set to the to my indexing set. So I want to have all the functions, I will call them V, from my totally ordered set to X, such that my for a fixed element of my set X, I cannot go outside of it many times. How do I explain? I just want to, like I will have a fixed element. So let's say that X is the natural numbers. And I want to have almost all the elements of V. Let's say my V is ... I want to have almost all of them being 0. I can have some numbers outside of 0, but almost all of them need to be 0. At some point, I will just have zeros all over it if my x0 is equal to 0. And given V an element of this set, I will describe as greater or equal to L. No, I would describe the element VL as just the restriction of all the maps of this element after L. So just going back to the drawing, here I'm describing, for example, let's say, here I have my horribles, right? So here I have the level 2, here I have the level 1, here I have my level 0, and here I have my level -1, right? So if I want to describe my element as V minus 1, I'm just saying that it's something that begins at the horrible -1, and it's the only element that will give me this path. So here I go through 0, then I go to 2, then I go to 1, and 1, and 1. In this case, for me, I need to repeat 1 over and over again. So when I get to this middle line, this infinite line, I'm already stuck at 1. So instead of describing my vertices on this tree as just, a node, I'm describing them as I have the function from the full line until my set X, and I'm just describing this function from a point onwards. So here I'm describing the function from the point -1 on the horrible -1 onwards. And because you just have one point that will have this complete path, this path here, each vertex will be described uniquely in a way. So these elements, these are the full, I'm just getting all the full lines possible, all the paths from one end to the other. But here I'm getting the vertices because I'm saying that I'm going just from one horrible onwards. I'm just talking about the path on one horrible onwards. So the pre-wreath tree will just be defined as the set of all these elements, all these vertices that are from one point onwards. And here it's just equivalence relation, which is what you expect. So two functions restricted to L and L prime will be the same if and only if L and L prime are the same. So, they are on the same horrible. And after this path, they always go through the same, they have the same things after that point. They never stop being the same on that point. So, and you can also define the order if two elements, one will be bigger than the other if the L is bigger than the other. And at the smallest of the L's, they are equivalent, So I'm just saying that this, for example, is bigger than this because when I restrict to the function here to the horrible 0, I get the same path as the horrible 0 had before, as the other one had from the horrible 0 onwards. And with this, we have the definition of the pre-wreath trees. And there are 3 things that are important on this definition. The first one is one of the uses that I have for the L on my totally ordered set is that I want to have an idea of something right next to it forward and something right next, some things, not necessarily just one, in this case, many, that will be back. But I know that I can take at least one step back always and always one step forward. I want to be able to do both. So one of the nice things that I have here is that I have the successor function. So here I have my v minus 1, right? That is 0, 2, 1, 1, 1, and so on. So the successor of it will be just the function with the same idea on it, but instead of having, you just erase the minus 1 part of it. So you begin at the horrible 0 instead. Another one is that you have a color function. For the ones that already saw, what are the name of the groups acting on trees? Bucket-Moses groups or stuff like that. They usually, to define the actions on the trees, you want to have a coloring on the tree. And because the way that this is defined, for example, here I have my vertex v1, right? Which is the one that we had before. I can define the coloring of it just to be what the value of it on minus 1 is. So in this case, the value of it on minus 1 is 0. So I already, with the definition that I had for these forests, in this case, it's just a tree, but in bigger lines, if it's Z by Z, it would be a forest. I already have a coloring inbuilt on the definition. And I also have a horrible function, which will tell me how far or how close I am to the thing. So the function already gives me naturally the horrible function, which, you know, here I'm saying that I'm on the level minus 1. Here I'm saying I'm on the level 0, on the level 1, on the level 2, and so on. So for the function here, it's written wrong. It should be getting the same function that I had before, v minus 1. So the horrible in this case would be just be minus 1 because it's the level that the function began. It began on the level minus 1. So it's on the horrible minus 1. So with these 3 definitions, we can start talking about how automorphisms of these ordered forests will act on the vertices of these three. So let phi be an automorphism of it, and let's say that VL is an element of the, oh, here it's lambda as well. It's an element of our tree, right? So let's say that phi of VL will be Wj for some other element, Wj of our vertex set. So the automorphism will always send the inner vertices of VL to the inner vertices of Wj, where the inner vertices will be just all the things that are pointing directly towards it. So all the elements that the successor of them will be the element itself. So, and these inner vertices, they are always in bijection with the set X that we are using for the coloring, right? So looking at how phi move the inner vertices from here to here, by looking at how these bijections on the set X are, we can define an element from the symmetric group of X in relation to this action. For each element of alt gamma, we can define an element, this element, for each element in alt gamma and each vertex on our tree, we can define how the colors on the inner vertex of these elements will be moving around. So And with this, we can finally describe what our group is. So if we have G at t.d.l.c as C group acting on a set X with compact open point stabilizers. So if you want to just think about discrete groups, you can just think about a countable discrete group acting on a countable set. For the case of t.d.l.c, let's say that you have a compact open subgroup of G that stabilizes an element X0 in X. So I will talk about this later, but and let L be a discrete totally ordered set without endpoints. We can define this group, the group that I want, which will be in the end just iterated with product, as all the automorphisms, such that I forgot to define SU. It's not here, but SU, I'm just saying that it's the set of all VLs, such that the action of our phi SU of phi. The action of phi on VL is not in our group U. So we are just saying that almost everywhere that I have on my group, my phi is acting as U, but in finitely many elements, it might be acting outside of U. And you also want the group to fix the horribles, because if I don't fix all the horribles, I can start to add too many elements and easily lose the locally compactness of my group. So here I will have a group that can easily be shown to be t.d.l.c, and that the idea is that I want to, from this group onwards, start adding elements to make it have the nice properties that I have. But at least this group, by what I understand, it should just be iterated with product of like L groups one after the other. And I think that's it that I have. So here are just the reference that I have. The first one is just a construction that already exists, which follows a similar idea, but in this case, your L is just Z. It's what I did in my thesis with Colin, George Willis, and Stefan. The second one is an article that I saw before that it's the idea that I'm trying to adapt now, because I have these constructions for elementary amenable groups, and I'm trying to, instead of just talking about groups acting on some sets, I'm trying to transform this action on ordered trees, ordered forests, and be able to build groups in a similar way to what they have. And here is where at least the first notions of pre-wreath structure is. So it's also where part of the ideas come from. And that's all I have for today. Thank you.
Thanks, JV. Does anybody have any questions or comments?
So this construction, it's still with the aim of finding elementary groups with bigger and bigger rank, right?
Yeah, like at least so far, because the idea is that, you have these with products, and the only thing that I need to build now is a way to, make these groups be compactly generated step by step. But the idea is that they are, how do you say? If I build them nicely, they are kind of one inside the other. So you can kind of, I don't know how to explain nicely. But what you do to one, the next one you might do that and a bit more, and then you can get a slightly bigger rank. And then you go for one that is a bit above, and then you just add a bit more things than what you did before, and you can get a bigger rank. That's the main idea that I have at the moment. And you have this general construction that, the construction that I had before, I had to iterate it, and on the iteration, you need to worry about many small details to make the iteration work well. In this case, it's not like I will need to be iterating the group. I just need to know how from these groups I can move them around and make them as nice as the other ones were. So I think having the process for one of them can help on the ones after as well. If it makes sense.
Yeah.
Okay, if nobody has any questions, let's thank JV again. Thank you.